All right, so we are going forward with part 2 of our nervous system lecture. We left off talking about membrane potential and how it's mediated through sodium and potassium's interchange between the sodium-potassium pump, separated, of course, by a plasma membrane. So it's all about the difference between the inside and outside of the cell. So we're going to move on or continue on and talk about graded potentials versus action potentials. So neurons, they use changes in the membrane potential as signals to receive, integrate, and send different information. The changes in the membrane potential can produce two types of signaling. You have your graded potentials that are usually incoming signals operating over short distances, and action potentials that are the long distance signaling of the axon portion of the neuron. So the graded potentials, again, are localized. They are occurring at cell bodies or dendrites, and the action potentials occur at axons and are conducted over longer distances. So these graded potentials are these small, short-lived, localized changes in membrane potential, either as depolarization or hyperpolarization. They are termed graded because the greater the stimulus, the greater the change in the potential. The graded potential is decreased in magnitude as the distance of stimulation increases. So basically, a small patch of depolarization will spread through this localized graded potential. So one area of depolarization will cause more areas of depolarization. And basically, you can see here, this would be localized active area, and then this is getting further away in distance. It basically shows that the strength of the graded response is strongest, localized, and then as you increase distance away from that localized effect, you decrease the amount of strength or efficiency of that signal. So it's decremental stimulation of a graded potential with increased distance. And this is these graded potentials are absolutely necessary for facilitating the full spread of an action potential. So local depolarization is facilitated throughout the whole neuron through graded potentials, which then helps facilitate an action potential, which is essentially a large change in the resting membrane potential that spreads over the entire surface of the cell. So this is your traditional nerve impulse. Action potentials are identical to the skeletal muscle cell model that we've been talking through. So they are initiated at an area called the axon hillock, which is basically right where the body of the cell turns into the axon. These action potentials do not decrease in strength with distance, so the strength remains constant over distance. And then action potentials will only occur if the neuron is adequately stimulated, which basically means that the localized cell has to be depolarized to negative 55 millivolts. So the original resting membrane potential was at negative 70. And you basically have to depolarize to negative 55 millivolts to get an action potential response. And the other thing with this is that this type of response is an all or nothing principle. So you either reach the threshold of negative 55 millivolts and you're depolarized and action potential happens, or you do not reach negative 55 millivolts and there is no action potential. There's no in between. You either meet the threshold and get the action potential, or you don't meet the threshold, you don't get an action potential. So it's all or nothing principle with these action potentials and depolarization between the neurons across the membrane. So this is a generalized kind of step-by-step along with a graphic of how this works a little bit. So within our resting state, you can see here we're going to work along this graph. So this is resting, depolarization, repolarization, hyperpolarization, back to resting. So right here, we're looking at the original resting state. All gated sodium and potassium channels are closed. Only that little bit of leakage runs through to help with maintenance. So there's a little bit of maintenance where some things are leaking out. So you're putting the other one through. For example, a little bit of potassium leaks out. So you put a little bit of sodium through or get the potassium back. You basically are just little mini balances, but this is all at rest. This is the resting state. Step 2, we're in a depolarization phase here. The Na plus channels, the sodium channels, are opening, rushing into the cell. So local current is depolarizing the membrane. The voltage gated sodium channels open and sodium rushes into the cell. The influx of sodium locally changes the local polarization, and you see depolarization progress to further areas of the membrane. And depolarization at the stimulation site reaches a critical level, that threshold of negative 55 millivolts, and depolarization becomes self-generating. Additionally, as that depolarization becomes self-generating, it will keep strengthening its own signal and keep further depolarizing. And this is a very good example of a positive feedback loop within our body. So basically, once you reach that critical level, you start depolarizing further in other areas that causes further depolarization, graded potentials, and it keeps building on itself in a positive feedback loop until you see depolarization of the whole cell and the release of an action potential. Step 3 here, we're looking at the repolarizing phase. So basically, the sodium channels are inactivated. Potassium channels are open. So you are now exchanging the potassium. You inactivate the sodium. So you stop the influx of sodium, and then you open up the channels of potassium. Potassium rushes out of the cell down its concentration gradient. So that's repolarization. And basically the internal negativity of the resting neuron is restored. So you've crossed that negative 55. You've probably gotten into around here. You're at between 0 and positive 30 millivolts. So you're basically exchanging those ions to get back to that original state, which was negative 70. And if you see, you actually go a little further. You go a little further than negative 70 here. So you're reaching a stage called hyperpolarization, where some of the sodium channel or some of the potassium channels, remain open and the sodium channels are resetting. So this extra potassium influx happens longer than is needed and basically takes the membrane potential below resting. So that's hyper, means in excess. So there's a slight period where you're down to about negative 90 instead of the negative 70 that you want, but it does balance itself back out so that you're back to 70 by the time this process occurs again. So basically, the whole idea here is that you're looking through the different states. In a polarized state, there is an basically even exchange. Sodium's on the outside of the cell. It's all positive. Outside the cell, negative inside the cell with potassium. Depolarization, sodium will rush in, changing the relative polarity. Repolarization, calcium or some sodium is coming in, but it's mostly being reuptaken. And then potassium is rushing out. And then with hyperpolarization, this is almost showing more of a balance, but really there is a state where there's a little extra potassium, hyperpolarizes, and then you reach this sort of more resting state here. It's not my favorite graphic, so we're just going to quickly move over it. I would encourage you to more so look through these if you need some help, but yeah, this is not my favorite graphic. Okay, so here's also putting it all together into one. So big picture between resting state, depolarization, repolarization, hyperpolarization, the differences between the channel states in these different states, and then what the actual steps are here. So resting state, all gates are closed. Depolarization, sodium's rushing into the cell. Repolarization, potassium's rushing out of the cell. Hyperpolarization, you're still seeing excessive potassium rushing out of the cell. Eventually, you meet a balance to get back to resting state. So we're going to look at how do we propagate an action potential. So they are propagated means sent or transmitted along an axon's length. An action potential generally causes the sodium channels in adjacent regions of a cell to open and produce action potentials. It's a domino effect. This is that positive feedback loop. So a single action potential causes the release of more sodium, which causes further depolarization in other areas. It causes more action potentials, which causes more sodium to open, which causes more action potentials until you're completely depolarized across the length of the axon. These action potentials are identically generated, regenerated, new, each membrane patch. And you'll see a continuous conduction pattern. This form of propagation is different than a type of propagation called saltatory conduction or saltatory conduction. This saltatory conduction occurs at myelinated axons. So what we're talking about here is unmyelinated. When it is myelinated, the action potentials will jump from one node of Ranvier to another node of Ranvier along an axon, which is basically the space in between the myelinated sheaths. So what we just mentioned is basically the first option. All this white text is within unmyelinated general options. So basically, this just illustrates so action potential is in the red, resting potential in the yellow, and then hyperpolarization is in the gray. So you see a depolarization or action potential, basically starting in a localized area and propagating along the length. So it causes further depolarization all the way along. And basically, the cell is doing its own thing in different areas. So you are where you were depolarized doing an action potential. Now you're hyperpolarized coming back to resting state. And here you're at resting state. Whereas other parts are going through different things. So basically, it's all kind of localized to its section, but then it travels across it. And this is the whole idea of graded potentials and how they get propagated locally from a positive feedback loop. So this graphic isn't a major point of what we're trying to get through, so we will move on here. But when we look at the conduction velocity, so how quickly can we conduct a signal? The rate of an impulse's propagation depends on two major factors. It's going to be the axon diameter. So the larger the diameter of the axon, the faster the conduction, as well as another factor being the degree of myelination. So the greater myelination, the faster conduction. Myelin insulates and decreases the membrane leakage, allowing for more rapid changes in membrane voltage. And this is coming back to that saltatory conduction. Saltare is a Latin word that means to leap. So the action potentials generated at the gaps of the myelin sheath have to leap from gap to gap. So here you basically have a cell body, you have an axon, and we have myelinated sheaths here in the blue. So you can basically see that the APs are only generated within the myelin sheath gaps, and they appear to jump rapidly from myelin sheath to myelin sheath. The myelin sheath itself prevents any charge from leaking extra sort of potassium or sodium, and this allows the membrane voltage to stay at a place that's very readily able to change. So you basically are jumping across these nodes, the space in between. This is the node of Ranvier, and these are the sheaths. So you're conducting in between the sheaths and jumping between them, basically. So here we're going to talk about something called the all or nothing phenomenon. So the all or nothing phenomenon, we did kind of I'll introduce a little bit here. It's the whole idea that basically action potentials either happen completely or not at all. So you have to reach a threshold of depolarization, which is about -50 to -55 millivolts. You see this threshold mark here on the graph. If our resting state is at -70 here at step 1, what we basically need to do is create a strong enough signal that gets us over this threshold. And once we do, an action potential is generated even as you further depolarize. But the whole thing of it is that if we get to -56 millivolts, just on the other side of this threshold, but we don't meet it, you do not see an action potential. This is all or nothing. There is no in between. It either fires or it doesn't. And the other part of that is what happens after it fires. There's this sort of period where it's hard to create another stimulus over the threshold to fire, and it's called a refractory period. So the refractory period is when there is a membrane patch generating an action potential and all the sodium channels are open. You cannot respond to another stimulus. Mostly. There is a small caveat of what will allow you to get another stimulus. We can see here the absolute refractory period and the relative refractory period. Basically, they have their different characteristics. So regarding the absolute refractory period, in this stage, you're basically during depolarization during the absolute refractory period from here to here. You are seeing large rushing in of the sodium. Oh, geez. Large rushing in of this sodium at this time. And you're seeing an action potential release because you're over the threshold. So basically, from a physiological standpoint, you can't rush in extra sodium and get over this threshold again because you already have sodium in there and you're already over the threshold. So basically, no secondary signal is going to stimulate a secondary action potential. No matter what you do, no matter how hard you try, during the absolute refractory period, there's no chance. From a physiological perspective, you're just already depolarized. You've already got a strong signal in the area. You're already over the threshold. You've already got all your sodium channels open. Okay. And that's for all the way through this light period up to this point. You can see after a while, about halfway through the repolarization phase, you get to this blue section here, the relative refractory period. So with the relative refractory period, basically at this step, the potassium is what's rushing in. Most of the sodium channels have closed and returned to resting states. Some potassium channels are open, but you're repolarizing. And basically, if you introduce a second stimulus that brought you above that -55 millivolt threshold, so if you were right here and you introduce something to bring you up to here, just theoretically, you would be able to stimulate another action potential because you would be able to get above the threshold, release the sodium, create an action potential. So that's pretty much it. So physiologically, it works out that you're below the threshold. So if you create a stimulus to get you back above the negative 55 millivolt threshold, and you can open up those sodium channels, you will create another action potential. So during the relative refractory period, if you have a strong enough signal, you can create a second action potential before you're at your ideal. Ideally, you would get back to over here and be back to resting before you did another. But it's possible to add to the first one. And you need a stronger than the negative 55 millivolt threshold to invoke another action potential during this period. So here we're going to talk about synapses. And we're doing so good. I'm so happy for all you all following along. We're getting towards the end here. So the synapse is basically the junction between two neurons, or between a neuron and its effector cell. So it could be between two neurons, or the space between a neuron and a muscle, or a neuron and some type of cell, whatever cell the neuron is innervated with. And there's basically three main parts. There's a presynaptic neuron, a synaptic cleft, and a postsynaptic neuron. So we'll go to the next photo and just kind of look at these real quick. So presynaptic neuron is right here. This is conducting the impulses. So it's basically receiving an impulse from out this way. It's propagating it towards the synapse. So it would end right here. So this is the presynaptic neuron. So say there's a nerve cell over here that sends a signal, travels up to this synapse. Okay. So presynaptic conducts the impulse towards the synapse. And then the space in between the two neurons, or the neuron and its effector cell, the space in between here is called the synaptic cleft. The synaptic cleft is a fluid-filled space between the neurons. And then step 3, or the third structure, is the postsynaptic neuron. So this receives the signal from the presynaptic and transmits it away from the synapse towards wherever you're going. So in our muscle example, receiving a stimulation from the brain up to this is the end of the nerve cell of the axon, releases the acetylcholine across the neuromuscular junction, across the synaptic cleft, which would then interact with the muscle cell here. So then the muscle cell would basically receive that acetylcholine signal, release the sodium, depolarize, and once it's depolarized, it would send the action potential down this way. So that is kind of the relationship between the synapse, presynaptic cleft, synaptic cleft, and postsynaptic cleft. Basically, this illustrates that there are many different types of synapses. So the axon is the part of the cell that would be innervating near the presynaptic portion, basically. So you can just see that there's different types of synapses. Axosomatic synapse is between the axon and the somatic cell body. Axoaxonic is between an axon and an axon. Axodendric is between an axon and a dendrite. And there are a bunch of different combinations of this. So neurons have anywhere between 1,000 and 10,000 axon terminals that are stimulated by an equal number of other neurons. So there's a lot of different combinations possible for this. We have two important types of synapses we're going to talk through: electrical synapse and chemical synapse. So an electrical synapse is basically the electrical current is directly transmitted from one neuron to the other through a gap junction. So electrical signal direct from one axon to another dendrite. Versus a chemical synapse where basically, oh, and sorry, by the way, I pointed to the wrong picture. This top one is electrical. Long lecture. I'm losing my own brain here. So anyways, the bottom photo here is a chemical example, chemical synapse. Chemical synapses are the most common type of synapse that we have. Basically, an electrical signal comes to the presynaptic, which then releases some sort of chemical messenger, neurotransmitter, across the synaptic cleft to the postsynaptic terminal. A really good example of this is when you get a nerve stimulation to the neuromuscular junction, that release of acetyl-CoA across the synaptic cleft interacting with the muscle cell, that is a prime example of a chemical synapse. And generally speaking, once the neurotransmitter does its thing, it starts to disintegrate. So the acetyl-CoA releases the sodium. So acetyl-CoA has done its thing at that point. It will start to reuptake or disintegrate. And then the sodium within here basically causes the action potential. And then the sodium will kind of have served its purpose. And the secondary point I'm trying to lead into here is that basically, a lot of times the chemical synapse will take an initial electrical signal, turn it into a chemical signal, maybe even a secondary chemical signal. But then once the chemical signals have served their purpose, they usually transfer back to a different electrical signal to then be conducted to the next step. So with this muscular example, you have an electrical signal releasing the neurotransmitter of acetyl-CoA, which then causes the release of the neurotransmitter sodium, which then causes an action potential to be released. So that right there is where the chemical signal turned back to an electrical signal. And then it's conducted down to the next synapse of the sarcoplasmic reticulum, where it's then turned into another chemical signal of calcium, and so on and so forth. So chemical signals generally will interchange between electrical and chemical, but there is a use of a chemical to facilitate its purpose, basically. So this is a general, so this is a little bit different from the muscle, but this is just generally how a chemical synapse works. So that muscular relationship is specific to the muscle, and there are nerves at a billion other places within our body. So, you know, this is the general formula here for a chemical synapse. Action potential arrives at an axon terminal of a nerve, which releases a chemical neurotransmitter of calcium, which causes the release of the calcium neurotransmitter into the synaptic cleft in between the two. Then the neurotransmitter will bind to the receptor site on the postsynaptic cleft. So the binding of that neurotransmitter will open ion channels of sodium and potassium that cause the graded potential change. The strength of that graded potential depends on the amount of neurotransmitters and the strength of that depolarization. And then basically the neurotransmitter effects are terminated once they have served their purpose. And generally, once you're opening all of those ion channels, you're going to see further depolarization and then generally transmission of a secondary electrical signal. So here is another graphic showing that. Action potential comes down the axon terminal. Voltage calcium channels enter, causing the release of a neurotransmitter that binds to the receptor site on the postsynaptic cleft, which causes the release or opening of some sort of graded ion channel, which eventually causes a graded local depolarization that causes a graded potential to further depolarize the cell until you have a full depolarization and a full action potential kind of sent along its way. And then after the neurotransmitter has done its job, it either gets reuptaken to its original spot, degraded by an enzyme, or just transported away through diffusion in some way, shape, or form. So a little bit more about synapses here. Postsynaptic membranes do not generate an action potential generally. There's this principle here of excitatory postsynaptic potentials, EPSP. Local graded potentials occur at excitatory postsynaptic membranes. If they're strong enough, that could lead to the generation of an action potential. And then there's also inhibitory postsynaptic potentials, IPSP, that cause hyperpolarization, so further away from depolarization of a postsynaptic membrane. This makes the postsynaptic membrane more negative and further away from depolarization, so far less likely to see action potentials from these inhibitory postsynaptic potentials. Excitatory can lead to the generation of localized graded potentials, which can lead to an action potential. But again, postsynaptic synapses will not create the action potential in and of themselves. It can happen through a secondary process with excitatory postsynaptic potentials, and it's unlikely to happen with inhibitory postsynaptic potentials. So we get to talk a little bit through neurotransmitters as well here. So neurotransmitters, they are chemicals used for neuronal communication between the body and the brain. They have functional classifications based on whether they are excitatory or inhibitory, and direct or indirect. So with the excitatory, basically it depends all on the receptor organ. For example, acetylcholine, ACH, is excitatory for the skeletal muscle, as we've talked about, but it's actually inhibitory for that cardiac muscle. And then direct or indirect. Does it directly bind to the open ion channels, or does it act through an intracellular second messenger? And most neurons will produce and release more than one kind of neurotransmitter. But these neurotransmitters, this is the language of the nervous system. The neurons communicate to process and send messages to the rest of the body. So when you think sleep, when you think thoughts, when you feel rage, when you feel hunger, when you remember something, when you move, when you smile, these are all controlled by your neuromuscular system and specifically neurotransmitters. So here we're basically going to talk through a few different pathway types, how nerves can interact with each other and how the pathway they take affects their relationship. So this first one here is called converging pathways. They involve impulses from several neurons coming together at once. They converge pathways increase the sensitivity to excitatory or inhibitory signals. An example of a converging neural pathway would be the converging of neurons from rods in the retinas of the eyes. This allows for increasing sensitivity to low levels of light through summation, which is a series of weak stimuli triggering an impulse. So these three can use weak stimulation to all three send a weak signal to stimulate this single cell. So that's converging pathways. Within diverging pathways, impulses from one neuron split to travel into several neurons. As a result, the original impulse is able to affect more than one destination at the same time. An example of this is controlling several muscles in the hand so that the fingers can work together at once. And then we've got what's called a reverberating pathway, where the neurons later in the pathway can link together. with earlier neurons, which allows the impulse to travel through the pathway once again. As a result of this reverberating pathway method, repeated stimulation of a pathway is possible for repetitive activities such as eyesight and breathing. So it allows you to keep traveling through the same pathway with multiple signalings for repetitive actions. And then finishing off here, we've got a few conditions to talk over. So multiple sclerosis, or MS, is an autoimmune disorder caused by the destruction of the myelin sheaths in the central nervous system. These sheaths become lesions that are called scleroses. And there's about 500,000 people in the United States that are affected by this condition. The onset is between ages 20 and 40, and females are about twice as likely to contract it as males. The symptoms include muscular weakness, abnormal sensations, speech disturbances, or even visual problems. And remission and relapse result in progressive cumulative loss of function. So basically, the myelin sheath is affected, so it's harder and slower to conduct your impulses. But the nerves themselves are not damaged, but the conduction is, and it affects the way you're able to signal. So that unfortunately is multiple sclerosis. The other one is epilepsy. So epilepsy is characterized by short, recurrent attacks initiated by electrical discharges of the cerebral neurons in the brain. Things such as light, noise, smells can cause these. And then skeletal muscle may contract involuntarily during a seizure or epilepsy. You may experience loss of consciousness. Generally, it's not associated with any intellectual impairment, but epilepsy has many causes, including brain damage, birth defects, metabolic disturbances, infections, toxins, vascular blood vessel disturbances, head injuries, and different tumors. And the last part here is basically just putting it all together, looking at a nerve cell. So you can see here, according to the outside labeled color, plasma membrane includes chemically gated channels within the dendrites in the cell body. Plasma membrane includes voltage gated channels within the axon. And then at the axon terminals, plasma membrane includes voltage gated calcium channels. So here at the dendrites, function is to receive the stimuli through the activation of gated ion channels in sensory neurons, generate or receptor potentials in motor neurons, and associated neurons produce excitatory or inhibitory postsynaptic potentials. The cell body receives the stimuli and produces those EPSPs or IPSPs through activation of chemically or mechanically gated ion channels. Within the junction of the axon and the axon, the integration of those EPSPs and IPSPs and depolarization, if you reach a threshold, will also propagate nerve impulses from an initial segment from the dendrites to the axon terminals. And then the axon terminals cause the inflow of calcium that is caused by depolarization of a nerve impulse and triggers different neurotransmitters. And that's a general overview, but overall, I hope that getting these out there and being able to look over them is useful to you all. And of course, if you have any questions, please feel free to reach out to me. But that is going to be all for us for now.